Patrick Cousins. I'm a software engineer at Etsy, and I'd like to talk to you all about sealed classes. I have to make a quick note. These views are my own. I'm not a spokesperson for Etsy, and these aren't official policies or anything. But I would like to talk to you about how I, and occasionally some fellow engineers, have approached taming state. And this is really a love story, given Andre's keynote. I thought I'd throw in a heart emoji. But yeah, so Etsy's apps have a lot of state. Our mobile apps have a lot of state. We have listings, tags, attributes, materials, variations, production partners, shipping profiles, payment methods, conversations, messages, snippets, lions, tigers, and even stuffed bears. OK, those last few may not have been state, but these are adorable. So all of these things form a matrix of possibilities that we need to track in our apps. If we get things wrong, then our buyers might fail to find a cat bed for Whiskers. And that's a world I do not want to live in. It's a very cute cat. It deserves a great cat bed. So how do we get a handle on this? So usually I try and start with a pragmatic approach, something like this, exclaiming help, followed by some desperate Googling. But it turns out desperate Googling does pay off. There are a lot of techniques out there for managing state. There's finite state machines, MVVM, MVI, MVC, Redux, Flux, Elm, Viper. These are all great ways of managing state. This is actually how I manage my state of hunger sometimes, but that's a little off topic. But anyways, none of these techniques quite changed our world like Kotlin sealed classes. And the nice thing about Kotlin sealed classes is they work with any of these architectures. They just are a way of modeling state, and they help complement any of these architectures. And as you can see here, I've proved mathematically that when you add sealed classes to these architectures, you end up with cat emojis. So it's great. So what are sealed classes? The official definition from the Kotlin docs is this. Sealed classes are used for representing restricted class hierarchies when a value can have one of the types from a limited set but cannot have any other type. They are, in a sense, an extension of enum classes. The set of values for an enum type is also restricted, but each enum constant exists only as a single instance, whereas a subclass of a sealed class can have multiple instances which can contain state. So this is a very precise but kind of wordy definition. To me, the important parts of this are they are restricted hierarchies, they are set, they are types, and they can contain values. So let's look at the basic example. You see this on a lot of blog posts and stuff. It's modeling maybe the response from an API. So you have success or failure, and we have two different types of items in the two branches here. We have a list of items or a throwable. Given that sealed class result, then we can use Kotlin's when expression to branch over this and handle the result. The Kotlin's when expression is often commonly described as a switch with superpowers. I think it's one of the language's most important features, and I think it's a lot like pattern matching. So we've done a lot here in just a couple of lines, so I want to go over each step. First, we are able to check the type of the result using Kotlin's is operator. This is equivalent to instance of in Java. Next, we were able to smart cast the result. So you can see that the IDE has given us a helpful little subtle green background because it knows those types are now of that. It knows those objects are now of that type. So we can use that data in a type-safe way without having to do any casting at all. The next thing we were able to do is exhaust all the possibilities for result. Typically, when a when expression must have an else clause. However, in our example, there are no other possible types for result. So the compiler and IDE know we don't need an else clause. So you could say, look, Ma, no else. So this is really important. This is exactly the kind of safety we've been looking for. And one of the great things about this exhaustiveness is that it helps you when you need to make changes. So if we look at what happens when we add a cancel type for our sealed class, then the when expression will helpfully know that we haven't exhausted all the possibilities now. We get one of those nice red squiggly lines that's really hard to reproduce on a presentation slide. So hopefully you all imagine that my straight line is very squiggly. So if we hover over that line, we actually get a very helpful message. When expression must be exhaustive. Add necessary is canceled branch or else branch instead. So the IDE already knows that we haven't covered all our bases here. And it even knows which possible types result could be based on the result sealed class. So hopefully the IDE offers us a quick fix to add the missing branches. There is one subtle difference here compared to the earlier examples that I showed, is that now we're assigning our when expression to a variable. And that's a requirement in order to get the exhaustiveness to kick in. You must use it as a value, a return type, or call a function on it. It's an important thing to watch out for, but it's a little bit of a gotcha. So if you really want to utilize the power of that exhaustiveness, you have to use it in some way. So another really helpful thing the IDE does is it shows us this little red light bulb for a quick fix. I think this is Alt-Enter for most people. Embarrassingly, I still use Eclipse keyboard shortcuts for about the past 4 years after switching to a JetBrains IDE. But hopefully none of you will tell anyone about that. So, but if you click on the light bulb, it gives you a few helpful fixes. You can add an else branch. You can add remaining branches. You can eliminate argument of when, or you can replace when with if. Adding an else branch is not really what we want. We want the exhaustiveness. Replacing when with if is also not really what we want. It does make the red squiggly go away, but that's not really what we're after here. Eliminating the argument of when is pretty interesting, but it's super off topic to this stuff. But there is one that is very helpful, and add remaining branches. So if we go ahead and click that, the IDE knows that canceled is the one branch we're missing, so that's what it adds with a helpful little to-do call. This inspection is very useful. So if we ever change our sealed class, all of our when statements that handle that type will get this little red squiggly, and this inspection will kick in, and you'll be able to use this to help you update and make sure you're handling all your cases. So let's look at both of them together. And to me, these are really two sides of the same coin. Basically, what we've done here is create almost a micro API, sort of a mini lexicon, for two pieces of code to talk to each other and have that contract that these are the only possible states that they're going to discuss. So that's the basic power of sealed classes, but let's dig a little deeper and see what else we can do. So let's take a new example called yarn. We'll have two items in it, cotton and wool. And let's create a new class, merino, and have it extend from wool. Merino is a type of wool, for those that don't know. Kotlin, by default, will actually not let us do this. We can open the class, but this should start to trigger alarm bells in people's heads. But what's interesting here is finding out what the effect is on our when expression. If we had written our when expression, if we were branching on yarn, have we created a new possibility? Have we created something new that we must exhaust? Maybe something like yarn.wool.merino or something else. And it turns out in this case we have not, because merino is still considered a part of wool. There are still only two possibilities and only two branches for our yarn class, wool and cotton. So that didn't really help us represent the hierarchy of what we were looking for, because merino is a type of wool and it's super warm. I highly recommend everyone try it. And in our imaginary sealed class of yarn type, we were able to make it a type of wool, but we weren't able to simultaneously make it a distinct branch. So if we wanted to treat merino more like a distinct material, this technique has not gotten us the ability to do that yet. But there is something else we can do instead. Instead, let's try a different approach, and we'll try nesting wool as another sealed class inside of Yarn. And then we'll also expand our example a little bit. We'll add alpaca as another very warm type of wool, and we'll throw in silk at the top level just to make it very clear what's going on. So now we've got what we're looking for. We see our friendly red squiggly line, and our quick fix is showing up like earlier. And if we were to go ahead and click that, then the IDE would add the 2 cases that we must exhaust. So this is great. This is exactly what we're looking for. Now our expression, it sees each wool subclass as a unique branch that must be exhausted. But there's one caveat here. If we write our when statement like this, and we check for the wool supertype, this is also considered exhaustive in this case by the IDE. So we don't get our red squiggly. And this sort of makes sense because we've handled all the top level branches for wool, but it's good to keep in mind so you don't get surprised. It turns out you can also, though, write it in a different way. As long as you're in the same file, you can write wool as a separate sealed class that it extends from Yarn without opening anything, as long as it's in the same file. And then, in this case, when we add our remaining branches, you can see they're named a little differently, but we still have to exhaust them. And in this case, wool by itself does not exhaust all the types. Excuse me. Need to have a little water here. So what can we do with this? Keeping with our example of wool, let's say we only want wool socks. If we use the when expression on Yarn, don't we need to handle all the cases? If we're just looking for wool, we don't really care about silk and cotton anymore. Luckily, the answer to that is no. You don't need to handle everything. Kotlin's standard lib will come to the rescue with a really helpful extension function that provides us a filtered view of the sealed class. So as an example, say we are processing a sequence of events. Let's create a fake sequence of all of our possibilities here. So let's say we're getting ready to knit a really warm sweater, and we have a view that is really only interested in wool. It wants only those wool socks. But it is interested in wool.merino and wool.alpaca separately. So how do we handle all these branches in our sequence? Luckily, Kotlin's iterable extension function, filterIsInstance, comes to the rescue, and we can filter the tree with a single line of code. And now, like magic, our when expression only needs to handle the wool branches. You can also do this with RxJava, and it's as simple as mapping down to the sub-branches you want. So here we can map from wool, and this provides the same filtered perspective of all the possible branches which need to be exhausted. An additional neat trick here you can use with RxJava is distinct until changed. Distinct until changed has a couple of forms as well. You can, oops, sorry, I think I jumped ahead here. It has a couple of forms. You can give it a key selector. You can give it a by function if you really want to get specific about what constitutes distinct. And the thing that's great about all this is that this when statement and the type inferencing and Kotlin handles this all perfectly. While this is more RxJava and while it's interesting in its own right, Kotlin is working and sealed classes are working great with all of this. So meanwhile, I'd like to get a little back to the example of how we actually used it. I began to fall in love with Kotlin sealed classes. And a fellow engineer named Cameron and I were tasked with implementing social sign-in for one of our Android apps. To be fair, it was mostly Cameron who wrote the code, while I spent all of my time trying to convince him to use way more sealed classes. What is social sign-in? I think nearly everybody probably knows what it is, but it's helpful to start with a definition, I think. like a lot of apps, we support letting our buyers and sellers log in via Facebook or Google, in addition to using their email or their username and a password. In addition to that, to help protect the security of them, we also offer the option of two-factor authentication. The last things on here may not be things we offer. But yeah, anyways. So social sign-in is also one of those features that it appears deceptively simple on the surface, but as you dig in, you realize there are a lot of steps going on here. You peel away layers, and you discover significant complexity. Social sign-in requires asynchronous calls to an external API, and there are several flows where the user leaves our app to go to another app, say to copy the two-factor code, and then they come back. And then finally, some of the flows are stateful. So if the user has used social sign-in before, we can skip the password step. But if it's their first time, we definitely want to ask them to put in their password so we can link their social account with their real account. This became so complex as we started looking into it, we decided to diagram it all out. Don't worry if you can't really read this. This slide was just meant to show you that this was a lot to keep in our heads. So we wanted to try and figure out a way to model this. So sealed classes became the perfect thing for us. Where did we begin? So there are 3 places where we make a call to a network or an API and await a result. This seemed like a really logical place to start because we didn't know how much we could use sealed classes in the beginning. So we just decided to start with this and model the 3 responses to these network calls. The first one we did is we reach out to the server after talking to the social sign-in code, and we modeled the response to that. Based on that, we make a request to actually sign in and model that response. One thing to note here that's different from my examples that I was showing earlier is now we're using data classes in the sealed class. Data classes are great for representing immutable value. They're not truly immutable, but for the most part, in practical purposes, they are. And then, so finally, we model when we hit the two-factor authentication endpoint. And here's all 3 of them together. So this is a great start, but let's look at what we have here. The first thing one might notice when looking at all this is that some of the states are the same or very similar. This is when we really want to resist our urges and instincts to combine these things. While they look the same, they actually represent discrete states that can show the user at different times in the flow. It's much safer and more correct to think of each state as different. We also want to prefer duplication over the wrong abstraction. There's a great talk by Sandy Metz and a great blog post. She is one of my favorite engineers, authors, speakers. But essentially, the gist of it is that poor abstractions have a way of tying your hands and forcing more abstractions in the future. And then a lot of those new abstractions tend to make less and less sense over time. You start abstracting over very, very unrelated things. I personally find this concept so important in practice that I'm like constantly pestering my coworkers about it to the point where they're just rolling their eyes at me now, and they know when I'm going to say it. But yeah, check it out. They are great talks. I highly recommend them. So if we go back to our code, you can already see that some of these states aren't actually exactly the same. So even if our instinct was to combine them, you can see we'd already be abstracting over different things. So in this case, not all success types get a token back. If we had made a single type, some of the handling code would have an extra parameter that it didn't care about. And it could, it's just extra typing at best, but it could confuse us and cause bugs at worst. And then in this case, sign-in result failure gets a token, while the two-factor authentication result gets an error message. If we had represented these as a singular failure type, it would be extremely easy to mix up these 2 strings, and it would cause bugs that are very hard to find. So it's definitely more correct to represent these as distinct things. And really what we're trying to represent is that someone got an error at this step. They tried social sign-in, then they went through sign-in, and then they got an error, which is really definitely not the same as getting an error at some point anywhere along the way. So if we go back to the code, the next thing we may notice here is that these states are sort of connected. For some folks, they might be starting to think about something like a finite state machine. And I think finite state machines are great, and it definitely might make sense. But what we've done here is define a very readable, safe way of modeling state. And something like a finite state machine is much more about having good transitions between state and predictable transitions between state. So something like sealed classes works great with finite state machines, but it's just a different part of the stack. And I've actually seen a bunch of finite state machine libraries effectively use sealed classes to help model state as well. So taking another look at the code, the 3 sealed classes are logical, and they match our 3 distinct API requests. Ultimately, though, this was sort of an imperfect representation. In reality, if we had wanted to perfectly match the diagram that I showed earlier, there would have been multiple instances of sign-in result for each branch, and multiple instances of social sign-in result, and multiple instances of two-factor result. So the point of this, though, is you want to be pragmatic. You want to do what works for you. For us, those steps provided the right level of abstraction for the refactoring effort that we were undertaking at the time. In the future, we may very well want to connect each and every branch into a giant single sealed class hierarchy. Instead of 3 separate classes, we'd use a single class that represented the complete set of possible states. So let's take a look at what that might have looked like. So this represents the complete state structure for social sign-in for our apps. And as you can see, this is already a lot of code. Certainly too much to fit on a conference side, although that was not part of our decision-making process, mostly. But more importantly, this was a relatively small feature. And now we have a very large tree of state. As we can imagine, if for a more complex feature, this could grow very, very quickly. And so, at the time, we stuck with the 3 classes. There are other drawbacks as well that people should watch out for. If you create a giant tree like that, then creating each state becomes very verbose. With each nesting, we have a bit more to write when we instantiate these things. If we didn't put it as one giant nest, but rather did it in the same file as separate classes, then you lose a bit of that visual representation of the pure tree structure, but it does make it a little easier to write when you instantiate them. You cannot have naming conflicts. So that's just another thing to keep in mind. But yeah, when you instantiate these things, they're a little easier to write, and it's much more concise. So there are definitely trade-offs with the 2 approaches. And again, be pragmatic. Do what works for you. So you'll need to weigh those trade-offs for yourself and for your users and for your features. So why do we do all this? Why do we spend all this time setting up state classes? And what about other patterns? Well, I'm glad to pretend that somebody asked that question. One of the things we really want to do is we want to compartmentalize the unknown. As long as our preconditions hold true, as long as they're a contract, then we can ignore the things that are not important and focus on the problem we're trying to solve. And in Kotlin, the way we do that is we lean on the language. We lean on the type system. There is much more value in a type-safe language than just avoiding type coercion. It not only makes our code more expressive, it moves that work to the compiler. And when we can move things to the compiler, it means we can focus on the most impactful things, like building better features for our users. So what about other patterns? Couldn't we do some of this already, like in Java? So I've always liked this quote. We stand on the shoulders of giants. It's a little cheesy. It's very cliche. But when you think about it, it makes for a decent analogy. It respects the achievements of people who came before us, the discoveries and hard work of great people, in our case, great engineers and computer scientists, who have figured out some of the hard patterns for achieving things like type safety. But it also captures the fact that we want to reach a little bit higher. We want to look at those best practices and patterns and evaluate them and see if they meet our needs and not just accept them for what they are. We use them to inform our tactics in creating better features for our users. So I wanted to say this first because there are a few patterns I'd like to go over that I don't think make a whole lot of sense anymore. For example, the visitor pattern. The visitor pattern was a way of achieving type safety and working around Java's lack of dynamic dispatch. There are some great things about it. It's polymorphic. It can keep things loosely coupled. And adding and removing new elements was just a matter of writing a little bit of boilerplate. There are some not so great things about it. It's a lot to keep track of in your head. There's lots of indirection, which means it can be harder to reason about, and it's not fluent or semantic. So, like, what is a visit? What is an accept? And how does that relate to the problem I'm trying to solve? The method names of the pattern, when you have methods named after the pattern rather than the domain you're trying to solve, it's just a little distracting. Sometimes you need that, but the more we can reduce that, the better. And it was very unfriendly to beginners. So I grabbed a visitor pattern example from Wikipedia thinking it would be long, not thinking it would be this long. And it was just to show, like, there's a lot of boilerplate here, and this is roughly the same number of branches as our yarn example earlier. There is a great video on YouTube that I highly recommend folks check out if they want to learn more about the visitor pattern. That could be, it's too much for this talk because it's an hour of stuff, but it goes into detail specifically comparing the visitor pattern to Kotlin's sealed classes. Highly recommended. Another option for achieving type safety is with a collection of heterogeneous types that is the delegate adapter pattern. This is mostly an Android-specific thing, so those who aren't Android engineers may not have heard of this, but in a lot of ways, it's very much like an implementation of the visitor pattern. The delegate adapter pattern, it does improve upon the visitor pattern in a few ways. And it does maintain a lot of the same benefits. It was a reasonable way of achieving type safety via an instance of and type ID check. It was more semantic, so the method names made a lot more sense, like is view for type, which makes a ton more sense than visit or accept. And it does work around dynamic dispatch. And it stays polymorphic, so it keeps things loosely coupled. But unfortunately, it does retain some of the visitor pattern's cons and adds a few of its own. So like the visitor pattern, it's still fairly a fair bit of boilerplate, and it's a lot to keep track of in your head. There's still a fair bit of indirection, and it's an abstraction over the adapter pattern that's already in Android, which already has an integer-based type ID system. It's also leaky, so when trying to pass references around, you quickly realize that you don't have access to the same resources that you would if you had used a more standard adapter in Android. Thus, you have to then work around the pattern, thus making it leaky. But again, we stand on the shoulders of giants. These patterns weren't wrong. They very much improved upon our ability to get type safety in looking through these heterogeneous collections of items. The delegate adapter pattern brought all that to Android and improved upon it. But to keep with my cheesy theme, we're standing on the shoulders of giants because we want to reach a little higher. And then just one more to look at is, a good old switch statement. A lot of people describe when as switch with superpowers, but it turns out switch can't even do any of this because you have to have constants for your cases. We can, of course, write a bunch of if statements to look like it, and it turns out you can use instanceof with those. So if we take a look at what that might have looked like, we can start to see why this might not be ideal. One of our issues here being that if we created a new type, say automatic car, instanceof would still evaluate this as a car. And we put any code that assumes this is a car at risk for unpredictable behavior. So an automatic car, for example, maybe it doesn't have a functioning drive method. Because it's automatic, it drives itself. So while we put in a check there for automatic car, we could put it in before instanceof, but now we're in a situation where ordering matters, and that's no fun. You could say that if an automatic car generates unpredictable behavior when used as a car, then it's dangerous and you should never get into that car because it violates the Liskov substitution principle, and I would say you are right. A very safety-conscious person at that. But I would also say it's better not to have to rely on your code always following best practices and other best practices for other types. But the question is, what are we trying to solve here? And I've started to touch on it a little bit, is we're basically branching on a heterogeneous collection of items. We're trying to run different code based on the type of each item. And polymorphism solves this by giving each item a common interface or superclass. But sometimes this forces us to create relationships that don't really make sense. What if all the items don't need the same method, or they're not totally related? And as we've seen now with sealed classes and when, our items don't need to have anything in common at all. You could also say, but didn't you say earlier that Kotlin's is operator is the same as instanceof from Java? And I would say, yes. But Kotlin makes all of this OK. All classes in Kotlin are final by default. So this makes it far less likely that somebody will actually extend a class and create automatic car, extending car, and accidentally trigger code meant for the superclass. And because types in a sealed class are not polymorphic, and there is no need to create interfaces just to have commonality between them, this removes the desire to do that, and it removes the dangers associated with that. So there's less of a chance that we'll make a mistake because we just put everything together in some supertype or with some interface. And then finally, branches can only be defined in the same file as the sealed class. So this drastically reduces the risk of someone might add a branch unwittingly and cause confusion elsewhere in the code. And that's it. Thank you very much.